Perfect. Thank you, Florence. So yeah, hey everyone, I'm Shri. I'm a first year student at Carnegie Mellon University studying computer science and robotics. Um, I work at a lab here where I look into training sim to real policies for dexterous manipulation. And so recently I got really fascinated by world models, and there's just been so much hype in this space and lots of really cool demos. So I want to spend some time talking about some of the things that I've learned about world models, and kind of just like trying to answer this question, which is like, why are world models suddenly becoming so big in robotics, and kind of where are we going from there? So I want to break at least this talk down to kind of four main parts, which are like kind of like what are world models essentially, and then like how do world models kind of increase like policy robustness, and why these models are useful, and then how we can use kind of like this idea of world models to like create like ideal robot policies that we can deploy in the real world. So I want to I plan to kind of like go back all the way to like the foundation of like world models and talk a little bit about the literature surrounding that, and then kind of just like look at like other places such as like autonomous vehicles and how like different other like adaptations of world models have been used to kind of help create this idea of generative simulation that we can train these policies on. So I want to go back to 2018 when David Ha initially kind of released this first idea of using neural networks to kind of simulate world models. One of the quotes that he kind of starts off his paper with is that humans develop a mental model of the world based on what they're able to perceive with their limited senses. Their decisions and actions we make are based on this internal model. So kind of the idea that he's hinting towards is that like for us humans, for example, when we choose to do a task such as like picking up a cup or maybe transferring something from one hand to another, we're not just simply kind of like looking at our hand directly or like kind of like the joint action space of our fingers. But essentially what we're kind of doing here is that we're able to understand the underlying dynamics of the world, which is like physics, for example. And so we can't just throw a cup and pick it up with the other hand, but we have to kind of stably move our hand from one side to the other. And kind of the reason why we really want to start thinking about trying to understand the world through like these internal representations is mainly because of the fact that simulation might not really be enough. And so generally the process for creating or generating large amounts of data and training a policy kind of comes from this idea where you can do massively parallel simulations through multiple policies, and kind of as you train this policy and gain like years and years of experience over like a couple of hours, what you essentially do is kind of this trick known as sim to real through something known as domain randomization, where the idea here is essentially you simulate a bunch of different physics parameters like your frictions, your gravities, and your contact forces to be able to hope that the physics of the real world essentially can be in the distribution of the simulation parameters you train. But some of the issues with simulation in general is the fact that most simulators are designed for rigid body dynamics, so for fixed motors and whatnot. But the thing is, like simulating like soft hands or like very like complex interactions is a very big engineering effort. So not only you have to kind of set up the environment here and set up your randomization parameters, but the issue is when it comes to scaling these policies and being able to generalize across multiple tasks, you're kind of handicapped by your own engineering effort, which kind of means essentially if you want to be able to be really good at every single scenario in the real world, you have to be able to engineer every single real world scenario in simulation. And that's generally infeasible. The other thing too is that your environments in simulation lack real world diversity. So there's this idea in simulation with respect to the sim to real gap, which is this idea that you want to be able to have the distribution of your simulator match the distribution of the real world. So for example, depth images have a low data distribution difference because of the fact that your depth images in simulation look pretty similar to your depth images in the real world. But for example, your RGB images in simulation might look very like a lot different compared to like RGB cameras in the real world because of lighting and occlusions and whatnot. And so kind of the question that world models are trying to answer is, instead of having to hand engineer every single simulation situation, or instead of having to hand engineer rigid body dynamics, can we just directly learn what the world looks like from raw sensor data? And so kind of the benefit here is that you're able to match the full complexity of the real world without these huge data distribution gaps. And so this was kind of one of the first ideas of using world models through something known as a variational autoencoder, where what you want to do essentially is, in this case here, we're learning how to drive in an OpenAI gym environment And essentially what we kind of do is we take like this bird's eye view image of where the car is, and we can encode this to a convolutional neural network to get kind of this latent representation over here that we see, let me turn the laser on. So you kind of have this latent representation here. And the whole idea behind this latent representation is that you want to be able to predict what the world looks like over time. And one of the ways you can do this is through creating this lower dimensional embedding space that encodes this real world data. And through this real world data encoding that you create through your latent space, you're able to not only use it to create a policy that can predict what the future would look like through the actions that it samples, but also is able to take in previous time step information and use information from the past to be able to update its own predictions, but also better understand how the dynamics of the real world change as it takes a certain action. So for example, in this car that's driving over here, maybe making a left turn would cause the entire world to warp left because the car's direction changes. And so as the policy iterates through more and more iterations, it kind of just notices that, okay, turning left might cause the world to turn left. And so this is just an inherent dynamics embedding that the model chooses to learn. And so just like a quick TLDR on variational autoencoders, the idea here is that given some sort of image or input that we can kind of just define as X over here, we want to encode this image to some sort of latent distribution space. But instead of directly predicting our latent vector, what we kind of do here is we predict the mean and variances of this latent distribution that we do sample from. And what this kind of allows us to do is also condition on this latent input, for example, where if I go back to my previous example over here, if I chose to maybe adjust what this latent vector was, then I get a different frame, for example. So what we kind of, it's not necessarily just a one-to-one pairing, but we allow for stochasticity to be implemented when we are able to specify our means and variances and be able to sample from that. In this case, because, in order to backpropagate through our random nodes, we need to be able to use a reparameterization trick where we simply make our latent variable just be the mean plus the variance times some fixed noise from a distribution. But based on this information, what we're able to do is be able to generate reconstructions of the real world. So in this case, we're just kind of optimizing for a KL divergence loss, where we're trying to reconstruct the real world environment given its frame through this latent space over here. And so the idea behind the original world model paper is like, okay, if I'm able to create a world model first that can reconstruct, then what I can do from this reconstruction is be able to sample the latent vector. And then from the latent vector space, I can use an RNN to understand the inherent dynamics of the world, and then use this inherent vector and use this inherent latent space to be able to create a controller model that can output actions. And so these are some of just the outputs that they get. One really interesting result is that you can kind of see how fine-tuning this latent vector causes massively different changes in the reconstruction of the image. So you can kind of notice over here that we have this original ground truth image, and then what we do over here is as we kind of modify the latent values of our vector, you can see how it changes the reconstruction. So for example, pulling a certain node might change the way the road is shaped, or it might change the curvature of it. And what's really fundamental about this is that if you really think about this idea of inherent world models, you want to be able not only to kind of fine tune on things like these, but also at the same time, it allows you to learn a lot of different complexities in the environment. And fundamentally, that's kind of what you're looking towards in a world model, which is, okay, am I able to not only just learn the dynamics of the real world, but also understand how it's changing the distribution of my latent parameters, allow me to change what I see in the real world. And so they also show it in a different task known as VisDoom. So here in this environment, the agent's supposed to avoid the fireballs shot by like these monsters. And we kind of just define the inherent reward in this environment to be the episode length. So the longer the policy is able to live for in this environment, the better it's able to stay. So in this case, you can also kind of see over here that we have these real environment observations, and then these reconstructions are upsampled from the embedded latent vector. So you can kind of see that we actually do get a pretty similar one-to-one like course like mapping here, where we're able to encode the real world into this latent vector, and then be able to show that, okay, this latent vector that we encode from actually is able to understand the inherent dynamics of the real world. But the thing is, the policy, the evolution, they use an evolutionary policy in this paper, and the thing is with an evolutionary policy, it's gradient free, so it doesn't really allow you to learn long horizon behavior and also get a better understanding of your dynamics model. And so one of the first implementations of being able to kind of back propagate through your network is through one of the Dreamer paper series. And so essentially what the Dreamer paper does is they kind of break down this idea of creating a world model that you can learn through into like three main steps, which is first learning the world and then learning the behavior. And then once you learn these two, you can learn to act in the environment. And so the first part here, when it comes to learning your dynamics from experience, the goal is kind of, you can kind of just think of this as like your agent it's a random policy that's just interacting with the environment. And so at each time step, you can use sample and observation, which in this case is like your image frame, and some arbitrary action, then you get a reward for it. The goal of kind of the model here is to be able to, again, perform like this reconstruction objective, where you want to be able to reconstruct what the next observation looks like, and then the reward along with the next latent space. And so this allows you to be able to build a world model in the sense of what the policy is doing in a sense. So for example, here, if I had the spider that was walking, I'd learn to essentially construct what the reward function would look like and how like maybe applying a certain action would change the dynamics of the spider. So for example, maybe if I had an action that was like, okay, move forward, then I should be able to inherently map this idea of moving forward into my embedding vector. And then once you get a good policy that's able to reconstruct your rewards and your ability to map future observations, then you're able to learn this behavior and imagination. And what's really interesting about learning this behavior and imagination is that you essentially only need your initial observation time set. And once you get this initial observation time step and you're able to encode it in the latent space, you can create a policy, an action policy that's able to learn directly from this latent space alone. So instead of having to resample for your observations and re-embed or re-encode your images and then pass it into your action policy, you can just simply directly learn within this latent space. And so it's kind of this idea of rolling through your latent space that the authors call as imagination. And so what would happen is that we're kind of simulating if we took some sort of arbitrary action, a hat one, then we get some reward, and then we just simulate through that. And from kind of these imaginary rollouts, we can learn a value function to predict the future return. And the really important thing about this is the fact that the model here that's being trained is fully offline. So once we're able to create this action policy, we can finally act in the environment directly, where we take this learned policy, and then at each time step, we take the current observation, and instead of having to do this imaginary rollout, we can just directly use the observation encoded rollouts. And so we can directly learn from the observation space to be able to deploy in the real world. And so the goal here is kind of broken down into like these three main steps here, where you want to do dynamics learning of your world model, and then learn the behavior, and then interact with the environment. And so kind of just as we talked about, the goal of the dynamics model is to be able to predict how the latent state evolves over time. And so what we kind of do over here is we first start by initializing this empty data set, and we kind of draw these batch samples of our actions, our observations, and our rewards over some fixed horizon. And as we generate these samples, we use the encoder to convert these observations into these latent states, which are SFT here. And so we're sampling these states from our previous state estimation, our previous action, and our current observation through the representation model. And as we do that, the goal is to obviously be able to predict future states. And we do this through this representation learning, which is kind of just a combination of your reconstruction loss, the KL divergence, and your word prediction error, which I believe they do define as the log likelihood in this paper. And so the goal here is that the step is essentially just kind of like this world model that they want to train to simulate the environment in space. And then from there, we kind of have like the behavior learning goal, where we want to learn some policy and value function purely through like these imagined latent trajectories. So we start from some arbitrary sample latent space. And then once we start from this latent state, we can imagine future directories by rolling forward with the world model. And based off that, we're able to predict rewards and the values from there, compute the value estimate, and then update both our action network and our value network. And the key thing here is that instead of training directly on the real experience, right, we can just leverage the world model directly to simulate these trajectories and optimize the behavior. And then from there, once we get a strong enough action policy and strong enough action value network, then we can use the train policy to collect even more real world data. And then from there, it kind of just like creates like this loop where you can continuously add data to your data set and then sample behaviors from it and iteratively just be able to make your policy better and the world model. So that's kind of like the main idea here, which is essentially like the more data you collect, the better your world model becomes. And so this is just fundamentally, in a sense, a data problem where you can just sample more and more data, get a higher quality understanding of your world model, and be able to then sample better latent spaces that you can then train this policy on. And so the authors show some pretty cool results. Unfortunately, they didn't really have videos on what this looked like over time, but you can kind of see over here that like they get pretty good reconstructions of their long-term predictions. So obviously the task that they were trying to solve fundamentally was if you roll out a latent space or if you roll out a latent embedding over time instead of using real-world observations, what does the policy actually kind of tend to look like? And so you can kind of see like in the beginning, it looks pretty good. And then as we like step forward towards like 30 to 35 steps, there are like slow like discrepancies kind of with the way the agent walks here in the simulator. But for the most part, it looks pretty good. And so obviously like this, it shows some really interesting results of world models, which is fundamentally that you can just simply not only just collect more data to create a better model, but to some degree, we're able to map long horizon tasks in a pretty accurate manner. And also at the same time, be able to understand the underlying physics behind the simulator. And so that to me is really fascinating because instead of having to hard code parameters about the real world, we're able to just simply learn how the real world operates through observation data. And so one thing some of the authors do is that there's some more follow-up work to this from a different group where they take this idea of the dreamer model and apply it directly to a robotics test. And so it's kind of the same framework again, where you have a world model and then this behavior learning through like these imagined steps, where in the world model phase, the daydreamer kind of takes in these high-level sensory inputs. So it takes in like cameras and then your joint proprioception data and encodes them into these latent representations through an encoder network. And then from these latent embeddings, they're able to use a recurrent state model that kind of maintains like these hidden states over here, which evolve obviously over time based off your previous states. And the whole point again is to create a dynamics model that learns how the world changes with respect to these actions, and then use the decoder at the same time to reconstruct these original observations. So you're reconstructing both the image and your proprioception data. And then in your behavior learning phase, you then use this learned world model to train the policy without interacting with the environment at all, given some arbitrary real sample. And so one of the issues the authors mentioned with the Dreamer paper was the fact that because the size of the input images were really big, predicting future inputs, if you go back over here with our reconstruction objective, it becomes pretty computationally expensive, especially since if you're using multiple sensors like your RGB sensors and your depth cameras, so having to reconstruct that every single time step can be inherently pretty expensive. And so Daydreamer uses a recurrent state space model, just like the original the world models paper, but uses like these 4 separate networks. So obviously the first one's their encoding network, the second one's their dynamics network that tries to predict the future latent state given the previous latent state and just the action. And then you also have your decoder network that tries to predict your proprioception and your input data, along with your reward network, where you want to predict the reward the agent gets in the next latent state given your current state. And so all of these kind of work together to model how the world behaves in the compressed space, and kind of to make sure that the agent explores a lot and doesn't just fall towards some sort of deterministic policy where it just kind of like picks like very similar actions at the same time. They kind of add this entropy regularization term where I believe they make n like 0.001 or something in the paper. But the whole point is that you want to be able to encourage your model to explore different actions and be able to not converge towards one fixed action that might not be the global optimum action. And so you can kind of see through the loss that we're able to learn how to balance like 3 things, right? Which is like first learn how to like create actions that lead to high rewards, and then learn from how like good or bad actions turn to be through like the advantage, the difference over here. and then also at the same time be able to encourage like randomness into the action so that it doesn't continuously get stuck at a certain action, but it allows it to explore a little more. And so in the paper, they kind of test out this idea in 4 different environments. And so they do one was like a quadruped walking, and then they use 2 different robot arms for pick and place actions, along with using a sphere for navigation in a contained environment. And the results also do look pretty cool. You can kind of see here that in like the top row, this is one of their latent rollouts on the UR5 environment. And you can kind of see over here that like it's trying to pick up this orange and like move it through time to like the other box. And you can kind of see that as it goes frame by frame, it slowly picks it up and moves it over. And then it does the same thing with the X-arm environment over here, where it learns to grasp and pick things up. And so they also show that they're able to create a pulse that's able to walk within an hour, which I think is really cool. And so it kind of just goes to show that one of the most powerful things about world models is that their ability to, or just because of the fact that their data distribution is very much aligned with the data distribution of the real world, you're able to just directly learn from real world data, allowing you to be able to scale posts. So in this case, like as it goes through and does 10 minutes, and now in 30 minutes, it's slowly starting to learn to walk. And then 40 minutes, it kind of moves. And then after 60 minutes, they're able to show really robust locomotion where they can add these forces on the side. And even though if they're able to tip the robot over, because of the fact that it becomes so robust to the real world, it's able to learn to get up and continue walking. So that's a really cool demos here. I want to kind of shift things up a little bit and talk a little more about where we've been seeing a lot of world models, which is in autonomous driving. And so this is Wave, a startup from the UK. They released I believe it's a paper called Gaia 2, where they kind of show that they're able to create these world models that are able to understand how cars operate in the real world, and then also be able to generate different types of situations. So autonomous vehicles, I think in general, can really serve as a really strong guide towards how we want robotics role models to be, in a sense. And Gaia does this really well. They kind of break down their architecture into 2 main components. So they have a video tokenizer and a latent world model. So the idea here is essentially you have this video tokenizer from 5 different cameras that they kind of show over here. And the whole idea is you want to be able to understand your semantic information across all these cameras and be able to encode them in some sort of way. And then the goal is from there, you want to be able to use that to create a world model that can take in the inherent latent space predictions that you create from your tokenizer, and then based off its conditioning with respect to the previous latent state, the actions, and like domain-specific control signals like specific times and geometries, to be able to predict actions that are able to move you forward in the simulator. So they kind of break this down. They break this video encoding down into these 2 main encoder and decoder steps. Note that, again, we're kind of training 2 things here, right? We're training a video encoder, and then based off the video encoder, we use that to train the world model. And so the way the video encoder works is given some arbitrary input video, the encoder calculates your latent tokens through a series of spatial temporal downsampling, which is just essentially a bunch of 3D convolutions across your entire image frames. So in this case, I believe it was like 24 frames being passed in at the same time. And so they perform this downsampling across these 24 frames to extract information not only with respect to each image, but with respect to all the images in the sequence. And then based off that, they use a transformer block to be with respect to each image in order to obviously like gain much more semantic information with respect to its scene and better understand what's going on. And then from there, they kind of also follow this VAE style of training, where once they do get to like this latent embedding, it's not just essentially a direct deterministic latent embedding, but they predict your distribution mean and your variance, and then you sample your latent distribution from there. And then they use this Dino distillation objective. And so Dino, I won't talk too much about Dino, but the whole idea behind Dino is that Dino is just this vision transformer that essentially learns visual features from images without like human annotators through like this teacher-student distillation process. And so in the case of Gaia, we're kind of using Dino as this model to there still are latent affordances to what the dyno affordances would kind of look like. And so the point of this is that it kind of allows you to better understand what your model is specifically paying attention to, in a sense. And so the point is, the authors in this case, they want their latent space to essentially be able to encode the primary details of the environment. So in this case, if it was cars or roads, you can kind of see like in some of these images that like roads are like labeled as like green and cars are blue and buildings are red and whatnot. And so the overall goal behind doing this distillation with Dyno is just being able to ensure that the semantic affordances you get as you run through these temporal downsamplings and attention blocks is to ensure that your information that you're getting is like not only high quality, but is relevant towards the task. And then from there, they do this linear projection from your latent space up to another dimension with 3D convolutions. And then from there, they kind of break up your upsampling into these two main transformer steps, which they call spatial temporal attention, which essentially means you have your standard like spatial attention transformer block. And then from there, they kind of do this temporal attention, which essentially just means that they transpose your output shape, where instead of, in this case of spatial attention, where instead of attending to every other pixel in your specific image, in the temporal case, you kind of fix like the index of your pixel and you attend to every other pixel with respect to all the images of that specific pixel. You can kind of see over here, like instead of it just being an image, it becomes like this vector that they kind of attended towards. So one of the reasons why the authors do this in this paper is to be able to ensure that when you're upsampling in general is a lot harder to get right compared to downsampling. The authors in this paper also use a GAN loss during decoding to ensure that the images they generate are realistic and similar to the input images. But the other reason is also because obviously you want to make sure that not only when you're making your pixels attend to each other within the image, you also want to make sure that when you have your pixels attend to other pixels that are across the entire frame, this just allows you to get a much more, I guess in a sense, more of a 3D understanding of your environment. So for example, if I was driving and I had, let's say, a bus that was like 45 degrees to my left, right? And if I took in these frames, I should be able to see in like maybe my front camera and like my left camera that both of them have a bus. And so as I'm performing as if I'm like going through these like transformer layers, for example, I should be able to see that, okay, like the bus in my left camera tends to like the bus in my front camera. And not only does this allow me to gain more semantically rich information, but it also allows me to better understand how the dynamics of these cameras move together over time to create a more realistic world model. And so the goal of the world model here is to kind of just predict the future latent space, just like all the other attempts at world models, given the past latent state space, action, and other conditioning inputs. And so essentially, we kind of just project each action to some sort of linear layer. And then we also have a conditioning vector, which is kind of conditioned on like spatial token positions, camera timestamps, and geometry. And we kind of concatenate these together and then run cross attention through them to be able to just better understand, obviously, like better understand like correlations with respect to your actions and other features that would be pretty important to learning your latent spaces. And so the authors use this kind of form of diffusion flow matching. I'll talk a little bit about that too. So diffusion, we know, is kind of this idea where essentially you iteratively add noise to an image over some amount of time steps, where you go from an image that's in the distribution of what you want to an image that's a sample straight from a normal distribution. And then essentially then you create a neural network that kind of learns to subtract the variance of the noise through your original image, which in this case is like a normal distribution, all the way back until you get to the image of your desired distribution, which in this case is images of cats, right? Flow matching is a little different. So the idea behind flow matching is that we want to instead predict the directions of which these pixels in this original image move towards here. So instead of adding noise, the point of flow matching is that we want to predict the vector field of which the direction that these pixels are moving towards. And so if you kind of compare this a little more, right, we know that in diffusion, obviously you have the forward pass and the backward pass. And so in the forward pass, we want to model some sort of noise distribution such that as we apply Q to the original image X, we get noisier images. And then we create a policy epsilon that's able to learn to predict the noise of the image over time that we iteratively subtract through. In flow matching, we want to be able to instead predict some velocity fields. So it's velocity network where we can take in some arbitrary noise distribution and time step, and then output the probability path that takes us to our predicted output. So where U is kind of like where this phi over here is kind of our position function. So if we go back over here, kind of like the positions of these pixels. And so the point is we want to be able to predict what this velocity field looks like. And so one of the ideas the author used in this paper is that we can kind of linearly interpolate the probability path. So if we go back even to like this image, for example, like we know that one of the blue pixels here at the beginning is like t equals 0, and then the blue pixel over here is kind of like at t equals 1. And so we want to be able to kind of like create this linear interpolation where, like, for example, if it was t equals 0.5, our pixel would be like over here. So instead of just randomly adding noise for like some fixed amount of steps, just like how we do in diffusion, we can instead kind of create this linear path where these pixels, or where we can essentially kind of control how these pixels get noise added to them or removed over time. And so if we take, obviously we take the derivative of both sides with respect to this linear interpolation, we get this following relation, which is x1 minus x0, which is our initial noise prediction. And then this kind of just becomes our learned velocity function that we're trying to match. And so we train our velocity network just to be a straightforward squared loss with respect to the ground truth velocities. And at inference time, we can just use basic Euler integration to kind of approximate where our final distribution x1 lies over time. And so again, this kind of just summarizes like the idea of flow matching, which is like you want to be able to have a pass compared to like this random walk. And like there's a couple of reasons why. Mainly some of them are mainly lies in the fact that training flow matching is just much more stable than diffusion, mainly because of the fact that the ODE that you're optimizing for this linear interpolation is not only just faster, but it's more stable because of the fact that you're not simulating the forward diffusion process as well. And then the other thing too that the authors have shown, and even in previous flow matching implementations, is that it's much easier to condition with respect to observations when you're creating a flow policy compared to a diffusion policy, mainly just because of the fact that it's more of a convergent path compared to diffusion. And so in the case of the Gaia paper, they use this idea of creating a velocity network to match the truth velocity. So they kind of sample context frames, and then from there, they linearly interpolate the feature latents with noise. And so the goal for the world model here is to kind of predict this target velocity of the in space, which then they can just train against a basic L2 loss. And so you can kind of see over here that the predicted velocity is this network where that kind of takes in your previous observations, your actions, and your conditional information, along with tau, which in this case is your kind of like time step here, and or not your time step, sorry, your average, and essentially from there you're able to kind of just do a straightforward L2 loss objective against the ground truth velocity that you can train a network to predict how you can condition on action. So for example, one of the other things this paper shows is that they can, if you go back all the way to the encoder, here they also show that instead of just using this sort of 3D convolution encoder, they can also just use an pre-trained clip as their form of encoding. And so this kind of allows them to be able to do things such as specifying certain types of generative simulations they're looking for. So they kind of show here, for example, that they can like generate scenarios of green lights and tunnels and overtaking cars, for example, which are really, really cool. I want to kind of end this talk talking about 1X. 1X is a really cool robotics company. This is Neo, one of their robots. 1X does a lot of cool things. One of the cool things they do is world models as well. This is one of the papers that they dropped, I believe, last week. So you can kind of see here, this kind of looks like, to me, this just looks like teleop data, but like in reality, this is just like generated world model data, which is really cool to think about because you can kind of see over here, we're able to simulate kind of these contact forces where the robot is able to put its gripper in the drawer and then be able to move it just purely based off pre-trained internet data and a very little bit of fine-tuned data. I believe it's maybe 60 hours of just teleop data they collected. And then over here, you can kind of see how it simulates clothes, for example, which is really, really cool to think about because clothes in a sense are not really rigid, and being able to simulate how shirts kind of like deform and fold is really, really interesting. So this is also kind of the 1x role model, pretty similar to some of the role models we've seen. They have an input video and then a video encoder, and then they also use this action encoder. So one thing they mentioned in this paper is that you want your robot policies to be action controllable. So instead of giving like loose directives like grab a mug or like pick up an object, you want to be able to create a role model that can actually react to the like agent's actions with respect to the laws of physics. And so what they do here is that instead of doing something like encoding with clip, they use the direct action encoded outputs from, for example, the teleop data that they collect to train this, to fine tune this policy on. So the policies, the video encoding stage of the network is obviously, again, like internet trained encoder and decoder, where they optimize, again, this reconstruction loss. And then they kind of add this action encoder to ensure that the video generated outputs line up with the actions that they put in. And so obviously, again, this is more VAE stuff where they want to, again, sample some mean and variance, and then they generate their latent embedding vector from there. And the other thing too is just to notice that this value over here is essentially they've kind of framed it as a binary solution, where in the initial frame they said the value to be -1 and the final to be 1 when it reaches this like success task, and then they kind of just use this temporal discounting backwards to assign the frame a certain value as it iterates through an episode. And so what they kind of show throughout this paper is that world modeling can allow for much faster evaluation and optimization. And so again, because of the fact that the domain distribution gap between the latent data policies and your real world data is really low, deployment can scale much, much faster compared to other solutions. And so in this example over here, the clips are kind of separated into image frames that are 4 seconds long. And then they use another vision transformer to encode the latent space. And at the same time, they're also able to sample on different actions. So if you kind of go over here, if you change the action encoder, for example, in the input actions, then you can do different things. So just given this initial state, they're able to show that by modifying the action inputs, you can have it do things such as like grabbing the mug directly or wiping the counter. So lots of ways to add stochasticity to the network over here. They show that just by conditioning on these generated actions, they're able to create different types of scenarios. And so in this case, these are just 4 of the scenarios that they generate. They also show that they're able to condition on this idea of navigation. So you can kind of see here that initially one of the policies that they train the world model on is picking up this box over here. And then they, by changing the action embedding input, they're able to instead make it so it picks up both boxes or the boxes on the other side. So that's a really, really cool action condition image observations over here. There's 2 failure cases that they show that are pretty interesting. One of them is that the world model that they've created still struggles with some interactions, and also with some contact dynamics. So you can kind of see over here in the real world data, the hand's kind of like petting this flower, but like in the generated reconstruction objective, the flower kind of flips. It's still pretty cool that they're able to kind of simulate this flower flipping, or the plant. But you can kind of see that once the plant flips, the hand just kind of moves in the air and doesn't really do much. So there's still like this bit of discontinuity with respect to not only just contact dynamics, but also this idea of scene understanding, where the policy fails to learn that the hand's just simply moving in the air and not directly touching a plant. The other thing they show that is that their world model still struggles with locomotion, and this is still probably going to be an active problem in world models for a little bit. And this is mainly just because of the fact that if you really think about like this idea of world models, when you're creating this policy where you're training in imagination, the issue is that once you sample your initial observation and then you roll the observation from there in your latent space, you're really prone to errors accumulating over time. And so in this case, you can kind of see that the moment an initial frame is slightly messed up or the latent embedding is slightly off, the errors propagate through time, and then you end up getting a reconstruction that deviates pretty strongly compared to what the original real world data is. So I want to kind of wrap this up just by talking about kind of the 3 main pillars of world models. And for me, that's kind of like being able to absorb obviously the entire complexity of the real world, and then also achieve production level evaluation. while also being able to deploy a lot faster. So one of the things even the 1X paper talks about is that if you had a robot that failed to brew a cup of coffee, um, how are you able to not only recreate the scenario as fast as you can, but also be able to generate like counterfactual futures and success likelihoods, given the actions that a model would take. And so compared to traditional simulation methods where you have to manually set up an environment like this where you have to simulate a robot maybe like brewing up a cup of coffee and pouring and giving coffee to someone, right? Um, Being able to do it directly through a world model just not only allows you to kind of perform these evaluations much faster, but again, because of the fact that the whole idea behind a world model is to be able to learn the embeddings of real world, your distribution gap is not as much as simulation. And so this just allows you to be able to kind of rapidly iterate policies much faster and be able to understand the dynamics of the real world better. Um, Obviously, we're still slowly learning and figuring out how do we create world models that absorb the entire complexity. So you can kind of see when we go to like the previous example, we kind of see that we still fail this kind of like contact dynamic example where we flip the plan entirely instead of obviously being able to kind of pet it. But one of the more interesting goals of world models here is that we want to be able to simulate this entire complexity and be able to better understand what are the dynamics of the real world that we can fine tune on in simulation. And so, for example, one of the ways you could do this is probably just by adding like an embedding vector with respect to maybe fixed hyperparameters of the world. So, for example, maybe you'd want to like introduce gravity as like an embedding constant that you could feed into our world model to better understand how the world works or things like that. But obviously, there's a lot of progress that needs to be made here. I just want to pull up this quote quickly from the 1X paper that they kind of use as they end their in their blog that they kind of talk about this vision where if you look at like ChatGPT, for example, right? Today, ChatGPT and all these really big generative like models have basically been able to create text that is pretty indistinguishable from real world human text. And the goal behind these world models is to be able to get to this ChatGPT point where you can do this with synthetic robotics data and be able to create synthetic robotics data in such a way that it looks identical to the real world. And obviously, some of the results we've seen so far are pretty promising, but there's a lot more that needs to be done in being able to simulate better contact dynamics and understanding the world better. But lots of really cool stuff on world models that are going on right now. But yeah, that's pretty much it. Happy to take any questions, and yeah, thanks for listening.
All right, thanks, Rita. That was awesome. Thanks so much.
Thank you.
Cool. Yeah, if anyone has questions, this is the time. All right, I'll break the ice then on the questions.
Okay.
Yeah, so you showed that robot that learned how to walk in like 1 hour. So I'm assuming that that's actually using like real data, right? Like somehow it goes back and learns, right? That's how it goes. But can you explain a little bit how that worked, or like?
Yeah.
Normally, like when you train models, like really, like you just when you train it for a while and then you put it out there, and then you get more data, and then you train it, and then you put it out there, right? So fine tune it. So maybe can you explain how that worked in that case?
So, kind of in this case, I can share my screen again. Actually, we can kind of go back. The algorithm loop is very similar to the dreamer model dynamics, and so this is kind of where. So if you go back to like that real world video, it's kind of the same idea here, where when initially you just take a bunch of random actions. So in this case, when you're learning the dynamics through your reconstruction objective, your policy is just stochastic. So you just take a bunch of random actions, right? And then just through these random actions, you can just take in the joint proprioception data, and then use some arbitrary reward function. And then as you kind of sample this reward function through and through, and as you collect more and more batches, then you can kind of update with respect to it. So in this case, with respect to like the real world example, what it's kind of the same idea here, where essentially like the once the policy is on the robot in the real world, like there's no prior information embedded into it. It just takes a bunch of actions from a stochastic policy, and then as it kind of like creates this data set of batches, then it can update its own weights with respect to its predicted reward, and then kind of using this representation learning, it's able to again be able to better understand the dynamics of the real world. I believe in like the case of the real world video, they already had a pre-trained world model, so that obviously like you're able to get faster
Yeah,
results. It was in this case they got it within an hour, which is pretty fast.
yeah,
But
that's pretty fast. And the other thing that was kind of amazing to me is that the like when you put a robot in a real world and it doesn't know how to move, then you get a greater chance to break it when if it does some kind of like a movement that's unexpected. So I wonder, yeah, I think I don't know how they did it, but like I remember a paper from Google from a while ago where they actually created certain algorithms where if the robot made like a move that would potentially break the robot, would practically stop
Mhm.
it. So I wonder if they have something like that where, because that's the big problem with the training robots in real world and not in simulation is that you can.
Yeah,
So I wonder if they have something like that where they applied some kind of a algorithm where, like, let's say, if the robot wanted to turn their leg like crazy and like on a certain
yeah,
direction, then they maybe they might have restricted that. So
yeah. They probably do have some like inherent like dynamic safety model to like ensure
yeah,
that like yeah the robot just doesn't like whip out like crazy torques out of
yeah, yeah, yeah. Actually, there's a video that went viral with this robot attacking his like researchers.
it.
Yeah, it was like all over the internet. But anyway, cool. Anyone else questions?
I had a question
Yeah.
for the neural network to ingest real world physics. How do you think that would happen?
So yeah, that's a good question. Even like to be honest, I'm not fully too sure how like what the ideal way to go about it. At least like the inherent assumption that all these papers make is that you can treat the physics of or understand the physics of the world as a data problem. And so just as you collect more and more data, then you like inherently you'll be able to understand the physics of the real world. And the reason why they do make this assumption is because of the fact that your your reconstruction models are trained on like internet scale large data. So essentially like these like vision transformers that you're seeing or all these encoders that you've seen like are not necessarily just trained on robot data, but they're trained on lots and lots of other data. So for example, like watching like videos of like maybe like people playing like basketball or videos of like um a dog running on like the grass or something. Um, and so the assumption here is that as you watch these videos and you construct next frame or next environment step predictions of these different types of environments, you hope to essentially like assume that the physics representation of the real world is embedded in like these latent embeddings. I don't know if that's fully the right way to go about it. I think it's a very interesting way. And I think because of the fact that we're able to process such a large scale of data these days, um, it could like really be possible that we're able to show some way that physics already is encoded within these latent spaces. I think one possible step in this space is obviously like conditioning your role models just based off fixed physics input. So I kind of mentioned gravity as an example. Like we know gravity is pretty much constant in Earth, assuming that we don't deploy these robots like anywhere that's outside of the Earth. But we could, for example, do things like that where maybe we could condition these role models based on certain priors, or maybe, for example, if we added semantic information, so using segmentation models like meta segment model, then we could be like, for example, if I was like, if you look at that 1x example where it struggled to kind of touch like the plant, if maybe we will just like segment the plant, for example, then we could add more semantic information that could allow the model to realize like, oh, I'm touching, like I'm like my hand is on a plant, maybe I should learn to touch it gently. Or maybe, oh, I'm touching a plant, that means that plants are pretty light. So in that case, the plant shouldn't like immediately flip over the moment you touch the plan. So I think there's a lot of ways to go about it. Mainly, I think right now the underlying assumption is that if you train on large enough data and like gigabytes and terabytes worth of like internet scale data, then you'd be able to inherently learn like the physics of the real world because of the fact that the domains of which you're collecting data from are just so diverse. But I think definitely there probably can be interesting ways to condition, whether it's on just like incorporating real world constants or allowing for more semantic understanding of your environment.
Thanks. Do you think crash test dummies could then be used to inform the physics based of real movement of robots?
Possibly. I'm not too sure. Can you talk a little more about crash test dummies? I'm actually not too familiar with that.
I guess with crash test dummies, most of them have sensors, so we know the inertia and how they move when they are crashing. So being able to use
Oh, okay. Yeah.
that type of physics.
Yeah, I definitely do think that's possible. Yeah. I guess maybe one of the things that you'd have to think about, and maybe in a sense, is probably cross embodiment, because obviously that changes with different robot arms you have, or for maybe like minor like deviations in your hardware, if that could accumulate with respect to how you simulate these robots. But yeah, no, definitely, I do think that's something you could probably condition on as well.
Thanks. That was my last question.
I had a question. I wonder if any of these companies or researchers talk about, of course, these companies as they scale to 1,000 or 1,000,000 robots, they are going to want to leverage the real world data and training that what they have already out in the field is experiencing. I think 1X is one of those companies.
Mm-hmm.
And it's just curious to see what how the problem may be solved, where you need to have I would assume you need to have very precise calibration, and things need to be basically completely working. And so as robots are out in the field and they age,
Mm-hmm.
and just like we do, we have to compensate, and how that will mix in with they're going to want you're releasing new bots that are great. They have wonderful, everything is new, calibrated and everything, and then you have the older bots that maybe aren't quite have to be calibrated a certain amount, but they aren't quite as good as the factory model as originally new. So it's just curious how, if people think about, okay, as I scale this up and I use all this learning data,
Mm-hmm.
how do I compensate for these differences?
So yeah, that's a great question. There's a lot of work on real world fine tuning, and there's this idea that you kind of see throughout, not just like in simulation, for example, but with even like imitation learning tasks, where if you train a network or like a robot to do something in like a simulator, for example, and you want to try to map it to the real world, right? Like the way you learn in simulation is kind of different to the way the real world works. And so what you might do is you might just have like this base policy that you learn in sim. And then once you have this base policy you learn in sim, you kind of fine tune with it in the real world. And so you let the policy kind of run in the real world, and then maybe you'll kind of like train the network based off like a couple like teleoperated examples to kind of like push the network in the direction of your real world data. And so I think at least like, whereas obviously like in this case, like the example that you mentioned about was like older robots and robots that might not be like as calibrated, like things such as like real world fine tuning really strongly help with getting closer to the desired, obviously like the desired position and the desired functional capabilities that you want. I think like interestingly, like a lot of world modeling stuff is, at least that I think, has potential to be used a lot in cross embodiment tasks, and just in general, I think it really allows you to be able to train different types of arms. So instead of having to create like this simulation where you can only train on one specific type of robot, you could possibly train on different types of robots. So if I maybe like, for example, if like 1X is like humanoid world model, which we kind of see is like pretty good. Like what if that was used on like Tesla's Optimus, or like what if it's used on like Figure's robot, for example, right? Like the underlying like changes, apart from maybe like height or basic other physical properties, the underlying actions and the state environments are not too different to the point where you can use a network or this reconstruction that you use on one robot and try on another. So I think just this idea of cross embodiment is really, really interesting, where instead of having to train on every sort of specific arm or every sort of like older arm or newer arm, you can just train on some sort of like arm that's kind of like in the middle of everything. And then from there, once you deploy it on a specific arm that might not be as calibrated as your desired arm, you can just kind of collect a couple of real world examples and then just fine tune with like teleoperation.
Okay, thanks.
Yeah, and there's some data sets out there that practically use like multiple, like you have like multiple robots, and then it's been demonstrated that if you train on like multiple types of robot arms, then it kind of generalizes and it can actually work better on one like a robot arm like this. So yeah, I think physical intelligence, they had some model that use some kind of open source. I think there's some open source data set out there with multiple robot arms, and then they demonstrated that practically you get better results if you're actually training on multiple types of robot arms. So
yeah.
I have a question for you. You mentioned at the end that relatively soon data generated by the world models would be or could be indistinguishable as human generated data, or real world data, I should say. And what are the best assumptions on how quickly that'll occur, and would or could LLMs help that come about quicker?
So I think there's been a lot of work with LLMs recently in trying to kind of just fine tune the synthetically generated data. There's definitely lots of like feedback loops that have been created. Even like things like clip, like which is like in this case like the opposite of like encoding. There's definitely lots of other ways to connect text with images. For example, maybe if you generate a synthetic image, or even like could you like have an LLM kind of try to explain through like what the image looks like, or maybe try to like explain if it sees any like weird outliers, and then compare that to maybe like a real world and kind of train like that. Or kind of like this idea of even like if you go back to like the idea of like GANs, for example, where you kind of have like a generator network that tries to generate these realistic images, and then you have like a discriminator network that tries that where this discriminator network's trained on both real images and like kind of fake images that kind of look like the real world data but isn't the real world data. And so you have this discriminator network that tries to kind of predict like, oh, okay, like if I generate the synthetic image, does it actually look real or not? And the whole point of this the whole point of this like GAN system is where you create images that look so realistic that the discriminator network kind of like fails to tell which ones are real and which ones are fake. And so I think there's been a lot of work with like LLMs. I think there's definitely a lot more work that will probably come out with respect to maybe using LLM as this way to fine tune, or maybe LLMs as a better way to generate images. So maybe, for example, could you like create better like latent embeddings of like words, and then kind of just use this better representation to create more realistic images. And so I think there's a lot of interesting work that's been done with LLMs. With respect to when synthetic robot data would probably have like this LLM moment where we create data that's so realistic that it surpasses or that it kind of like becomes indistinguishable. To be honest, that is a good question. I'm not too sure entirely. I do think we've definitely made a lot of progress in synthetic data generation, especially ever since we've been able, especially with like transformers and being able to better encode our understanding of the real world through these networks. I do think it's definitely not something that's going to happen within like the next year or so, but I do think maybe within a couple of years, as we make more and more breakthroughs with vision, I think as maybe, for example, as we find a better way to align ways to kind of extract information about the real world. So instead of, for example, like instead of just using like an image to be like, okay, wait, this image is what the real world looks like, could there be better ways to encode what this image actually means, and or like encode what are like what encode, sorry, kind of like encode like more like information about an image. So maybe there's like certain geometries that are really important that like you just can't tell from a straightforward RGB image that you'd want to be better at encoding. But I do think, yeah, to kind of just summarize, yeah, I think LLMs have, there's been a lot of work with LLMs and trying to generate better synthetic images and using it as like this closed like feedback loop where you just generate an image and be like, okay, wait, is this image real or not? Or if not, like what are kind of like these weird outliers about this image that I generate that aren't real? But I definitely do think there's been a lot of progress in this space, and especially kind of like this 1X demo kind of just shows that they're able to create these world models where they can simulate like realistic renderings over time.
Yeah, that's interesting. I appreciate it. I would have thought that maybe it can't happen now, but that the LLMs could help in the encoding and defining process, and maybe helping the world model train so it knows the appropriate action to take, since the LLMs have gotten so much better at avoiding the false realities that were so prominent in 2022 and early 23.
Yeah. I think also if you look at, so if you kind of go back to like the Gaia paper that I talked about, the self-driving paper, where they kind of like showed these results where they conditioned based of like, oh, overtaking or like stopping at a light or something. I think like LLMs kind of allowed for a better sense of communication with respect to like humans, instead of having to directly like modify like latent like vector outputs. You can directly modify your input text and then have like better aligned videos towards it. I do think the bottleneck is with respect to accurate physics simulation. So I think it's like not necessarily just a synthetic data generation part, but I think it's also at the same time a physics problem, where essentially instead of just creating, because you don't want to essentially just create a singular image, right? The whole point behind creating like these world models is that you want to be able to kind of create like these like video frame of data where you can kind of map out how the world changes over time. And so that necessarily isn't really just a straightforward synthetic data generation problem, but also how do you keep a synthetic data generation consistent with the way the real world works?
Yeah, precisely. No, interesting. Appreciate it.
Thank you.
All right, Jason. Listen.
Yeah, thank you for the presentation. This was great. On kind of the thread of what Michael was just asking, are you familiar with Moravec's paradox?
No.
Oh, okay. Well, I'll skip that. Basically, it talks about how sensor, motor, and perception skills are really difficult computationally, and I'm just trying to figure out what granularity, because fine motor skills, I guess, are really difficult to replicate. So I don't know if that's a thesis that they're making that goes beyond that or not. But kind of to segue that to what Michael was also talking about using and combining language models. You guys were talking at the beginning about the Gemini models that were released. I guess those are vision, language, action models.
Yeah.
And being multimodal. But then kind of also the other one that's kind of interesting is the NVIDIA Cosmos Foundation model that's out. And so I'm just curious, like where what you're talking about falls within maybe what the state of the art is for large world models today.
Yeah, that's a great question. So I think VLAs and world models are really, really interesting in the sense that when you think about these vision, language, action models, right, the vision and language part of your VLA is trained on the internet, right? So you use like something like some sort of vision encoder that's obviously like trained on like thousands and thousands of images. That's also paired with language text to kind of extract more semantically rich information. I think, yeah, so that like even with these like Gemini demos that I think are really cool, obviously I think like kind of like how this ties in with like world models, to kind of just answer your question, if I think I'm answering this right. I think there's some of the interesting things about VLAs and just like these vision encoders in general is the fact that they're really robust to just data in general, and like some more so in the sense that even if you create like a synthetic image that doesn't look like that realistic, yeah, like these VLA models are able to kind of reason through pretty well about like what's kind of going on in the image. And so in a sense, I think VLAs are really good in the sense that they're very robust to image obtrusions, or like, for example, if I kind of blocked a part of the image or like blurred up a part of the image, like you still have a model that's able to semantically reason pretty well. Or even if not semantically reason pretty well, it probably could learn, like, for example, like, oh, like this part of the image is blocked, like do not like walk forward in that direction or something like that. I think with NVIDIA Cosmos, so Cosmos, I think the Cosmos release was really, really cool. I think what makes it interesting in a sense that they do lots of synthetic data generation where it kind of falls again. I think I feel like Cosmos in a sense falls more closer to simulation than I'd say world modeling in a sense, because the way that they do their transfers across using like, I think like Omniverse, which is like an actual simulation agent, instead of just using like pure world state prediction. But I think also at the same time, I think the Cosmos world models were only 30 seconds long, which might be plenty in some sort of situations, but obviously at the same time, you do want to be able to roll these policies out for longer. And I think that's something VLAs also do struggle with at the same time, where you kind of aren't able to do tasks that are like minutes long yet, because of the fact that as you kind of progress over time, you start to lose information about the original goal and kind of how like the previous actions you're using build up towards the current actions. And obviously there's things like action chunking and all these other like long horizon like tricks that you can do to better create policies that train longer. But I think there's but yeah, I'm not sure if I fully answered your question, but yeah, I think some of the role models really does like tie into kind of this whole VLA models. I think even like 1X uses that uses this whole like VLA thing. It's a pretty big topic in robotics right now, especially because of the fact that we have so much data, and then with things like world models and simulations, and even like things like Cosmos that are able to create scenarios pretty well just based off using VLAs and LLMs to better understand what environments would look like. But yeah, no, I do think there's a lot of really interesting stuff there too. I'm not sure if I answered your question though, so let me know if I did.
It's so the only thing was like what the context of what you're talking about pertaining to some of these other developments. So you talked about world models, and then you also are talking about reinforcement learning with the robots and how it's actually learning basically mechanics and also the physics associated with it, right? Because these things have accelerometers in them, I'm sure, and then they can validate and measure those to predict physics based off that. But they're learning in real time.
Right.
So how do these other models fit within the context of that? I don't think you talked about VLAs.
Yeah. So
yeah.
So VLAs essentially kind of solve like a different problem compared to world models, which wasn't too much of the focus of this talk. But VLAs kind of do tie into this idea of being able to kind of embed the real world physics. So obviously, I believe like VLAs in a sense kind of also follow this inherent property of world models, which is that because of the fact that your vision model and your language model are trained on like an internet scale, like such a large scale of data, you're supposedly able to inherently encode the dynamics of the real world within your model. And so obviously, like if you were to like put an image of like in ChatGPT or something, for example, of like a basketball that was like in the air, like it would obviously be able to reason and tell you that the basketball is like going to fall on the ground because of how gravity works. And so I think inherently, obviously, we haven't been able to fully condition VLAs on true physics of the real world. And I think that is an interesting area of research because that also does tie into world models in a sense where if you can kind of embed this idea of putting physics in both a VLA and a world model, then not only are you able to kind of create a stronger policy that aligns with how the real world moves, but when you fine tune, so for example, like most VLAs are pre-trained, right? And so even like, for example, if you look at like physical intelligences, like VLA models, they're mainly trained against like a really big data set. And so when you kind of like train, if you were like able to fine tune with like a world model, in this case, you can kind of mix in this idea of like using imitation learning and reinforcement learning to not only create a policy that like has the knowledge of the internet, but you can also use the knowledge of the internet to become even better in the real world, if that makes a lot of sense.
Yeah, and what you're saying about the vision stuff makes a lot of sense, because I mean, I've done physics, and the thing is, right, you can actually look at images and you can watch a basketball fall and you can predict what the physics are. But if you have a world model, then that gives you a frame of reference on top of it where you can validate the perceptions, which I think is awesome. So that's very helpful. It gives it context. Thank you very much for your explanation.
Thank you.
All right. Any other questions? All right. Well, thank you so much for the questions, first of all. Awesome questions, awesome answers, and awesome talk. Thanks so much, Sri.
Thank you.